Okay, now, so if you remember on Wednesday, we started studying the B field in matter. We didn't really discuss it in detail how it comes about, but we had seen that if you have a magnetic dipole in a B field, so it will also rotate in the direction of this B field. So the total B field will basically receive two contributions. One, the one created by the currents that you have created, either inside your material or somewhere else, plus the B field created by this aligned magnetic dipoles. And we define this, if we have a medium, we just pick up some small volume where we average over. So, I mean, if you remember our discussion in electrostatics also, when we are talking about fields in matter, we don't really look at the microscopic fields at the microscopic scale, at the subatomic scale, because that field is fluctuating very rapidly. What we do is we just average those fields, so average out those fluctuations, so we have to obtain a kind of a smooth field. And to averaging this, what we do is we just assume a volume much smaller than the size of the macroscopic medium, but at the same time much larger than the atomic scale. In this volume, there will be some total magnetic dipole moment. This is the magnetic dipole moment of all the dipoles within this volume. Then we define the magnetization at the point R. Well, this volume is around the point R as, let me call this delta mu, delta mu over delta V. So this is how we define the local magnetization at a given point. And then, of course, if we want to find the total vector potential at some arbitrary point, so this vector potential, as I said, it will receive two kinds of contributions, one from the currents that you have actually created, and then a second contribution from all the magnetization in your system. And at the end of the day, we saw that this magnetization just kind of behaves like a current density, which is given by minus the curl of M. So the curl of B, now this plus the curl of M. The curl of B, which was 4 pi over C, now this, we also have a C over here. Now the curl of B, which is just 4 pi over C times the total current, this just became 4 pi over C. We have the free current plus this bound current. And so if we wanted to define a field just like in electrostatics, we define this D field, whose equation only dependent on the free charges that we put. We also want to define some field which depends only on the free current. So what we did was the curl of B minus 4 pi M. This was equal to 4 pi over C times the free current. Now just the naming, B is called the magnetic induction. And this quantity, which we called H, magnetic field. Intensity. So that was basically it. When we have a medium, it will be magnetized under the, if we create some current around it, and hence the total field will depend on both of these. And the current that is created, the magnetization, we can also just parameterize it in a sense in terms of this bound current. Now, one example that we can consider, let's say uniformly magnetized sphere. So we have a sphere. Let's just assume that it is magnetized in this direction. This is M. So what will be the field? Now, instead of this magnetization, we can, as we said, we can just use the corresponding current, JB, let's say for our, inside our sphere, this is curl of B, curl of M, but M is constant, so the curl is 0. There is a surface current. This was minus N cross M. In this case, let's say this is our z-axis. M vector is M0 in the z direction. N vector, which is the normal from inside to outside, is nothing but the radial vector. So if you just look at this point, this is our hat. At that point, this is on the surface, this is our M. This angle over here is theta. So the surface current is minus N cross M. What is the direction of this N cross M? N cross M is out of the screen, that is minus phi hat direction. So there's another minus, so this is in the phi hat direction, and the magnitude of N is just 1. The magnitude of M is M0, and the angle between the two, sine theta. Which we can also write as M0 R hat cross phi hat. No, R hat cross Z hat. So let's check the directions. Minus R hat cross Z hat. But you see, this is nothing but the, right? Or let's write this in this form, M0 Z hat cross R hat. So there is only a surface current density which has this magnitude. Well, does this ring any bells? This surface current density? So at this point, the velocity vector was omega cross r. No, sorry. R. So the surface current density at that point is Q times, or sigma times V, sigma omega cross r, where sigma omega is nothing but sigma times the magnitude of omega in the z direction. So basically these two problems have the same surface current densities. And hence the corresponding magnetic B fields and the H fields will be, the vector potential will be identical in both cases. And we had already solved the below problem.
How did you arrive from the current density, the expression for the current density, to this, to the surface current density?
Here you mean?
Yes, it's from JB equal to curl M to the expression below it. How can you link them?
Well, you see, what we had shown on Wednesday was that there is the volume current density JB, which is the curl of M, and there is a surface current density, which was C times minus C times N cross M. So this is what we had shown on Wednesday. So I know that there is no, in this problem, inside there is no current density because magnetization is uniform. But nevertheless, on the surface, there will be a surface current density.
So this assumes that there's no magnetic induction field around the receiver, right?
No, we didn't make any assumption. The only thing we claim to know is the total magnetization of the system. We say that, okay, the system has this magnetization. Why? We don't know. I mean, how was it created? We don't know. It might be a permanent magnet, for example, that will have a kind of a uniform magnetization. Or we could have put it in some external magnetic induction field, which created this uniform magnetization. We don't know how it is created. The only thing we know is that there is a magnetization, a uniform magnetization in this sphere. That's given to us. And then we said that, okay, if there is a uniform magnetization, we can describe it as some current density, that bound current, effective bound current density. And inside our sphere, this bound current density is 0. On the surface, it is non-zero, given by the last line. Then the next problem is, given these currents, what is the vector potential? What is the B field, etc.? So once we determine the B field, we can talk about the H field also. And then we said that, okay, let's not repeat all the calculation. Well, we will repeat the calculation anyway in a moment. But we just said that, okay, there is this current density, but this current density is the same as the current density of a sphere that is uniformly charged on the surface and rotating with a frequency omega. Then what we had already solved this problem on week 9, if I'm not Friday on week 9. So we can just pick up the solution. Or we can redo the solution. That we will do later on. Now, again, if you remember our electrostatic discussions, what we had done was we had defined this D field, which was E minus 4 pi P. Then we said, okay, so the P is proportional to the electric susceptibility multiplied by the E field, etc. Well, we will basically do the same thing here. So we have in our case, we have the B is equal to H plus 4 pi M. And we will say that M is equal to magnetic susceptibility times this H field, the magnetic field intensity, chi M this time, this is the magnetic susceptibility. So that B field just becomes 1 plus 4 pi chi M times the H field. Or B field becomes mu times the H field. This whole thing we call mu. So this is our new equation that gives us the relation between the D and the H field. In the case of electrostatics, we had the D field was equal to epsilon times the E field. Now we have the B field, which is mu times the H field. So we already know our equations. We know that the divergence of B is equal to 0. The curl of H is equal to 4 pi over C J free. We know now the relation between the B and the H fields. And given the boundary conditions, we can solve this. That's basically what we will do, a couple of examples today. Now, a couple of things we have to do before continuing is, in general, what we have is we have some material inside some other material. So, and okay, one boundary is at infinity, and we have the space is filled with one material, which can be the vacuum. Inside this, we put some other material with some other magnetic induction. And if you remember again in our electrostatics discussions, what we do is we just solve these equations in one of the materials, then we solve it in the other material. We divide our regions into various regions, domains. We solve our equations in each one of these domains separately, and then match the solutions at the boundary separating these domains. But that, to be able to do that, we still need to know what are the matching conditions. And the matching conditions we can derive from both of these equations. So we know that the divergence of B is equal to 0. This is always true, whether there is a boundary or not, whether our system is homogeneous or not, etc. But if this is nothing but the Gauss law for the B field, B dot ds over any closed surface should be equal to 0. This should be true for even a surface, half of which is in one boundary, half of the other one is in the other boundary. So if you just remember what we do, if this is our region, if this is our interface between two regions, this is our boundary, so we just assume such a very small cylinder on the surface. This is length d, this length d, the top and the bottom, let's just call the area A. And from this condition from here, we know that the B outside minus B inside, that n should be equal to 0. Why? Well, there are no contribution to the B dot ds integral from the side when we set D go to 0. So that the left-hand side of this equation just becomes B outside minus B inside, scalar product with the normal vector to the surface. The normal vector arises because the top and the bottom surfaces, their area vectors are perpendicular to the surface, but the perpendicular vector is n. And the top and the bottom, the area vectors are pointing in opposite direction, so that's why we get the minus sign. This is the left-hand side, the right-hand side is already 0. So this is one condition we have. And the inside and the outside of the surface is defined by our choice of n. So n points from inside to outside. This is our n, this is inside, this is outside. It's up to you to define the direction of n. You can just change the direction of n, but that means you are basically changing the definition of your inside and outside. So this is just like, if you just compare it with the analog expression in electrostatics, in electrostatics we just, the right-hand side of Gauss' law was not equal to 0. So on the right-hand side, instead of 0, we had the sigma. Now then we know that the curl of B, curl of H, is equal to 4 pi over C times J. JF, let's say. Well, from now on, I will just drop the F. Whenever I talk about the J, I will be talking about the free current. Now, in this case, the integral expression corresponding to this law is just if you integrate H dot dl over any loop, any closed loop, this should be equal to 4 pi over C times the total current enclosed by our loop. Now we still have our surface. This loop we can choose such that one part of the loop is on one side, the other part is on the other side. Let's say at this point there is a surface current running into the screen. Let's just assume our orientation is such that the current is running into the screen. Well, we basically have two independent choices of loops. we can choose our loop such that the two sides of our rectangle is parallel to K, to our current. But that basically means that there is no current running through my loop. The current is running parallel to my loop. So the right-hand side is 0. So this equation basically tells me that H inside minus H outside, if our loop is parallel to the current, this should be 0. Do you see how to derive these results? I mean, I'm not repeating them because we had already discussed it a couple of times before in electrostatics. Now, this component in the direction of K, what we see is the B perpendicular to the surface is continuous across the surface. The component of H in the direction of the free current is perpendicular to the surface, is continuous, sorry. Now the component of H parallel to the surface and perpendicular to K. So let's also study that component. We can just choose such a loop. Let's say this is D. This is also D. Let's just choose our n vector. This is our n vector. So this is inside our surface. This is outside our surface. Now when we set the D goes to 0, there won't be any contribution from the sides. But we will receive from these two sides perpendicular to my surface, but I will receive two contributions from the sides that are parallel to my surface. Now let me define this vector over here as my m hat vector. So B, this tells me that B inside, H inside minus H outside now this H inside is in the opposite direction of M. So there's minus H inside plus H outside scalar product with M vector. Well, this should be equal to minus K. 4 pi over C. Why minus? If you just consider the sense of my loop, the current is running in the negative sense. So that's why I have a minus K over there. Or I can write this as H inside minus H outside, that M is equal to 4 pi over C times K. Now let us look at my vectors. You see M vector is nothing but N cross K hat. So let me write this in that form. H inside minus H outside dot N hat cross K hat is equal to 4 pi over C times K. Well, let us try to combine these two. What do we know? That H inside minus H outside, let's say the parallel component, the component parallel to the surface, basically would have two components, one in the direction of K, but the component in the direction of K is 0, and another component in the direction of N cross K. Because if you see our surface is two-dimensional, we have these two unit vectors, k and n cross k. So any vector parallel to the surface can be written as a linear superposition of these two components. They are perpendicular to each other. It's just like our coordinate system at that point on the surface. Plus the component in the direction of n cross k, which is 4 pi over c. Or this is equal to 4 pi over c n cross k. Or let's write it in this form: the outside component minus the inside component, the inside H field, parallel to my surface, is equal to 4 pi over c times k crossed n. So this is just a short way of writing the previous two results. So now we also know how to relate the H and B fields on both sides of our surface. Now, in general, for most of the problems, we will not have a surface current. So this will be just 0. The parallel component is also 0.
But also we won't have bound current density.
It's already inside here.
I mean,
The bound current, we will have it on the surface.
yeah, it will always have been the surface.
Well, if there is a magnetization, there will be a bound surface current. But the effect of that bound surface current is already in H. So H will be continuous even if there is a bound surface current, as long as there is no free surface current. Now let's do our example. Let's assume we have a sphere with magnetic permittivity mu. It's an empty space. And outside, far away from our sphere, we have a B field, which is uniform. So we can just choose our z-axis to be in the direction of our B field. So B0 will be just B0 in the z direction. Now the question is, what is the H field, what is the M field, what is the magnetization of my system, etc. Now let's go back to our equations. We know that the divergence of B is equal to 0, both inside my sphere and outside my sphere. Curl of B, curl of H, this is also 0 because there is no current, free current. And we also know that B is equal to mu times H, both inside and outside. Or if you want, H is equal to 1 over mu times B. So curl of 1 over mu times B, this is equal to 0. Well, I cannot just take the 1 over mu out of that curl expression because mu is not constant over all space. But I can divide my space into two domains, inside my sphere, outside my sphere. In both of these domains, mu is just a constant, so I can just take 1 over mu out of the curl equation, and that would just give me the curl of B is equal to 0. So let's say this is region 1 and region 2. So in region 1 and 2, mu is just constant. So curl of 1 over mu B which will be equal to 1 over mu times the curl of B, which is 0, and hence curl of B is also 0. Both inside and outside. Not on the boundary, but inside and outside, curl of B is 0. So divergence of B is equal to 0. Curl of B is equal to 0. Separately. On the boundary, it will not be 0. Well, since curl of B is 0 in my domains, I don't need to worry about the vector potential. I can also work with a scalar potential. So I can say that curl of B is equal to 0. This just tells me that B in both regions can be written as minus the gradient of some scalar potential. As long as curl of a vector field is 0, it is always the gradient of a scalar potential function. So I already solved the second equation.
Why does one sign?
Convention from electrostatics. Well, the first, if I want to solve the first equation, then the Laplacian of this phi m should be equal to 0. Both in region 1 and region 2. I know I can use spherical coordinates to solve this problem, and the general solution of the Laplace's equation in spherical coordinates, I can always write it as ALM times r to the L plus BLM divided by r to the L plus 1 YLM of theta and phi. But you see, my function, my potential, or my system, nothing depends on phi. So this scalar function phi m should also be independent of the coordinate phi. But that tells me that in this sum, where I'm summing over both L and all possible L and m values, only the m is equal to 0 term can survive. And the m is equal to 0 term is just of YLM. This is proportional to PL of cosine theta. So just from the beginning, I can say that my scalar magnetic potential, both in region 1 and in region 2, should have this form. For some coefficients AL and BL. Now let's impose our certain other boundary conditions. For example, we know that inside the sphere, phi m is finite at r is equal to 0. So which basically tells me that these BL terms, which diverge at r is equal to 0, cannot appear in my expression of the potential inside my sphere. So phi m in region 1 will have this form. This is my solution in region 1. And in region 2, phi m should go to minus b0 r cosine theta as r goes to infinity. Because as r goes to infinity, I'm away from my sphere, and away from my sphere, b is just a constant. So the corresponding scalar potential should be just minus b0z. And z is nothing but r cosine theta. Well, this already tells me that phi m2 in region 2 should have this form, minus b0 r cosine theta plus, well, you see, if you look at this general expression, as r goes to infinity, BL terms, they go to 0 anyway. So this boundary doesn't impose any restrictions on the values of B, but it restricts the values of A. So AL, R to the L, only the L is equal to one term can survive as R goes to infinity, and that term should be just minus P0 R cosine theta. Remember, cosine theta is P0 cosine theta. P1, sorry. So that is why only the L is equal, only P1 should survive in my expansion. So this is the contribution from the A terms, plus I have the contributions from the B terms. So this is my potential in region 2. Well, you can think of these two terms in this way if you want. You see, the first term is already the applied external B field. The total B field will be the external B field plus the one created by my sphere. Due to the magnetization of my sphere, it will become magnetized. And that additional term is the second term, the summation over there. That is my additional term. Now, inside the sphere, inside my phi field, inside my sphere, well, the L equal to one term receives two contributions from my magnetization and from the external B field. And the other terms are only due to the magnetization of my system. So now we have these two potentials, one in two different regions. So we had already imposed our boundary conditions at the origin and also at infinity. The only thing left is just to match these two. So what do we know on the boundary? We had already derived the conditions on the boundary. The perpendicular component of B should be finite, perpendicular to the surface. Well, the perpendicular direction to our surface here is the radial direction. If this is n hat, this is nothing but r hat. So BR, which is nothing but minus d phi m by del r, is continuous on the boundary, which is at r is equal to capital R. So if you just take the derivative of phi with respect to the radial coordinate and just place small r is equal to the radius, whether we use phi m1 or phi m2, we should get the same result. So let's just take the derivatives. L A L times L r to the power L minus 1 PL of cosine theta. This should be equal to minus B0 P1 of cosine theta. Well, I'm just dropping that minus sign. The minus the left-hand side and minus the right-hand side should be equal. Minus sum over L BL times L plus 1 over R to the power L plus 2 PL of cosine theta. So these two should be equal. Well, if this is satisfied, the coefficient of PL cosine theta on both sides should be equal. So for L is equal to 1, A1 should be equal to minus B0 minus twice B1 over R cubed. L not equal to 1, AL times L r to the power L minus 1 should be equal to minus BL times L plus 1 divided by r to the power L plus 2. So these are one set of equations relating these coefficients A and B from the continuity of the perpendicular component of the B field. But we also know that since there are no free currents in our system on the boundary, on the surface, the parallel component of the H field should also be continuous.
Why did you
And the second one. Well, you see, B0 is the coefficient of P1 only. So what I did was all the coefficients of all the PL should be equal on both sides. Well, the coefficient of P1 has a different structure than the coefficient of other PLs because of that first term, B0, P1. This term only contributes to the coefficient of P1. That is why I only have minus B0 for L is equal to 1, which is the coefficient of P1, but I don't have that term for other L. Question? Okay, so we know that there are no free currents, so H parallel is continuous. Well, the parallel component of H parallel to our sphere is just we have the theta component in the theta hat direction plus the phi component in the phi hat direction, but the phi component doesn't exist because our phi m depends only on theta, so the phi component is 0. So this H theta should be continuous. Well, H theta, remember this is 1 over mu B theta, which is equal to minus 1 over mu 1 over r del by del theta phi m. So if I take the derivative with respect to theta of our potentials, it should be continuous across our boundary. And keep in mind that mu is 1 outside my sphere. It has the value mu inside my sphere. So let's pick up our potentials. So these were our potentials. This is phi 1. This is our phi 2. And so just take the derivative with respect to theta, multiply it with the 1 over mu of that region, and equate the two at this when small r is equal to the radius of my sphere. So that gives us 1 over mu, sum over L, AL, r to the power L, del over del theta, PL of cosine theta, should be equal to minus B0 r del over del theta P1 of cosine theta plus or minus L B L over r to the power L plus 1 del over del theta PL of cosine theta. Well, just like PL of cosine thetas are complete and orthogonal to each other, their derivatives are also complete and orthogonal to each other. So the coefficient of the derivatives of PL cosine theta on both sides should be equal to each other. Which basically tells us that 1 over mu times A1 R should be equal to, this is for L is equal to 1, this should be equal to minus B0 R plus B1 over R squared. Or 1 over mu times A1 should be equal to minus B0 plus B1 over R cubed. This is one equation we have. Well, just a warning. The B0 appearing over there is not the L equal to 0 coefficient. Okay, some bad notation. Sorry for that. But that B0 is not the L equal to 0 component, but it is the magnitude of the B field. And for L not equal to 1, we have 1 over mu AL R to the L. This should be equal to plus BL over R to the L plus 1. And this is our other set of equations relating A and B. Now let's look at our previous expressions. And compare it with our current expressions. You see, this equation for L not equal to 1 and this equation for L not equal to 1. You see, the last line tells me that AL and BL should have opposite signs. This equation tells me that AL and BL should have the same sign. Well, two constants can have both the same sign and the opposite sign only if they are 0. So this already tells me that AL is equal to 0, BL is equal to 0 for L not equal to 1. So I have these summations over all possible values of L from 0 to infinity, but actually there is a single term that contributes. Now let's find that term. So this is one equation between A1 and B1. And this is the other equation between A1 and B1. Now let's solve the two. We can just pick up A1 from the last term, put it in the second line, put it in the first line. We get 1 over mu minus B0 minus 2B1 over R cubed. This should be equal to B0 or minus B0 plus B1 over R cubed. Or let's see, we have 1 minus 1 over mu of B0. This should be equal to B1 over R cubed multiplied with 2 over mu plus 1. Or B1 is equal to mu minus 1 divided by mu plus 2 B0 times R cubed. This is our B1. And A1, this was equal to minus B0 minus 2 B1 over R cubed. And this is equal to minus B0 minus 2 mu minus 1 divided by mu plus 2 B0, or minus B0 times 1 plus 2 mu minus 1 divided by mu plus 2 This is equal to minus B0 mu plus 2 mu minus 2 divided by mu plus 2. So A1 is equal to minus B0 times 3 mu over mu plus 2. This is my A1. This is my B1. Now I know everything. Let me write my potentials. Phi 1 M. This was, if you remember, this is AL, R to the L, PL of cosine theta. Only the L is equal to one term survives. So this is equal to, well, A1 is minus B0 times 3 mu over mu plus 2 times R cosine theta. Let me write it in a different form. This is minus B0 times R cosine theta plus minus B0 or minus B0 times 3 mu over mu plus 2 minus 1 R cosine theta minus B0 R cosine theta minus B0 times 2 mu minus 2 divided by mu plus 2 R cosine theta minus B0 R cosine theta minus twice B0 mu minus 1 divided by mu plus 2 times R cosine theta. Well, the reason why I separated into these two terms is, well, the first term is nothing but the phi m corresponding to the external B field. The second one is the one that is created by my material. And if you see, that is proportional to mu minus 1. So if there is no material, mu is equal to 1, there is no magnetization, as it should be. Now, if you would calculate the corresponding B field, the corresponding B field is equal to minus the gradient of phi m1. This is nothing but plus B0 in the z direction plus twice B0 mu minus 1 divided by mu plus 2 in the z direction. And keep in mind, this is nothing but, this should be B, or let's say, no, let's just keep it like this. Now let's look at B2. Now phi m2, if you remember, this was minus B0 R cosine theta. This is the one we applied, plus the one created by this material, which was BL over R to the L plus 1 times PL of cosine theta. But we know that only B1 is non-zero. So phi m2, this is equal to minus B0 R cosine theta. Now B1, we had already obtained it. This one over here. So this is R, small r. So this is B1, 1 over R squared times cosine theta. Or let me just rewrite it in a different form, mu 0 R cosine theta plus mu minus 1 over mu plus 2 B0 R cubed R cosine theta divided by r cubed, or minus b0 r cosine theta plus mu minus 1 divided by mu plus 2 r cubed b dot r over r cubed. Or if we define m to be mu minus 1 divided by mu plus 2 r cubed times b, phi m2 is equal to minus b0 r cosine theta plus m dot r divided by r cubed. You see, the last one is just similar to the potential created by an electric dipole. And if we calculate the corresponding B field, this will be B0. This is from the first term, plus 3m dot r hat minus m divided by r cubed. The second one would be due, the first one is the one we apply. The second one is due to the magnetization of our system. Well, we also know that H was equal to B minus 4 pi m or B was equal to H plus 4 pi m so outside obviously m is equal to 0. So B2 is equal to H2. Now let's look at inside. We know that B is equal to 1 over mu times H, which is at the same time H plus 4 pi m. So m, the magnetization of our system, we can just calculate it as 1 over 4 pi times 1 over mu minus 1 times H. Or this is equal to 1 over 4 pi 1 over mu minus 1 times mu b. We already know what b is. M is equal to 1 over 4 pi 1 minus mu times b. Well, I know what b is inside. No, this is not B. Yeah, this is our B. Times this one. basically have a uniformly magnetized sphere. B is uniform inside, so M is proportional to B. It's a uniformly magnetized sphere. Well, the thing that you should do will be more or less what we already did in electrostatics. We know an equation for the B field, divergence of B is 0, the curl of H is 4 pi over C times the free current, and we know how to relate B and H field, so we can just combine all of these, obtain an equation for B or the H field. Then you have the boundary conditions. Most of the time, I mean, for example, in this problem, there are no free currents, so that kind of simplifies our calculations because we can define a scalar potential. Otherwise, we wouldn't be able to define a scalar potential if there are currents running in our system. So we could define this scalar potential, and then just after that point, it's exactly equal to the case of electrostatics. The only difference is that the boundary conditions will be slightly different. Questions? Okay, so let's give a 10-minute break and we will continue after the break.